I'm going to take next quarter, which is considered a 212, which is highly based on this class, which is let me just check what class it's called. It is called this 113, which is Introduction to Conventional Boot. So I decided to study all this because that's what my 3D print is done. So that's my plan, and better than listening to all these songs, basically. So I'm just going to check my song list, and then start doing this stuff. Now I'm going to bring a whiteboard in because that's how I'm going to study with you. Yeah, because why not? I mean, if I'm going to study at home, why not just post it as like a section? So all credit goes to Dr. Sanchez. Obviously, he's the one that made this book. I was shocked that he made a book about this in 2017. But yeah, all credit goes to this guy, this man over here. Gonna study. I did take a class before, so it should be easy just looking at this stuff. Yeah. Hopefully, I understand it. Now that's a different question. Do I understand it? Yeah, that's different. This might even voice hearing. I hope it records. Let me just check. Hello. Yeah, we're good. We're good. All right. How do I start the sharing? I think I need to stop sharing real quick, and I need to bring up the whiteboard over here. How do I bring a whiteboard? Okay, we have. So we start with the Navier Stokes. Obviously that's the kingpin above. Yeah. Obviously continuity, the conservation of. So, the thing we have to think about is the continuity equation, which I should have it memorized, but the professor literally provides it over here, so I should probably just write that to what the professor wrote. But let's go blind. Obviously there's a partial derivative of density, and then that is the first portion, which is the change in density. I don't know what's it called actually. Is it called a acceleration term? I think it is because it's a time dependent. So it's like density derivative or something. And then we go with the gradient of density and velocity like this equals 0. Now this is the form that the professor gives. So let's unpack it. How do you move in this tablet? Is this how you move? Okay, figured out how to move. Okay, we're good. We're good. We figured it out. Okay. So if I were to unpack it, now think about this. So this is really equivalent to the, it's not really writing really great. Let me erase this. Oh, yeah. This is disaster. This triangle is equivalent to dxi, which is the form I like to write it usually. Index notation is always what I like, but yeah. And then we see that the density is not constant. Oh, that's why she did that. Oh well, fair enough. But then we have to do. Let me. So what is this index notation then? Index notation xi. I know. I'm an old man. Density is not a is a scalar, but it has some it's now a derivative factor, so we're going to leave it in here. But to make a scalar out of this, it probably has to be a dot product. Now vi is like this. So I think, yeah, that's it. So that's equivalent to saying derivative x parentheses density v x direction, yeah, plus density x in the density vy direction. There we go. Plus density wrong y and density z parentheses density vx direction equal. Okay, that. So so this equals that. So let me just. How do you do back? How do you do go back out here? This I forgot all about how to do this stuff. So it's dot density v this. Okay, we got that. We got that idea down. So to fully write this, because we should write it fully, density t density plus density with respect to x. And I don't really like how I wrote it earlier. I honestly like it writing like this, but it was too big for me to fit it earlier. But now I know how big it is, so it's going to be something like this density vx. This is the way I like it to write it usually. Density vy, let's say density y plus density. I like it in this notation because it's compact, but when you visually see it, you have to write it in this form first. Now this is correct. This form is correct, but you can kind of see where the collide. Oh my gosh, this tablet. Oh, it's giving me the heebie-jeebies. This is equivalent to say density x I, and then we do parentheses density vi. Okay, am I correct about that? Yeah, and then you can write this. Yeah, oh, I hate tablets, man. They're the worst. Density vi v. How do professors do it? Like what the? Okay, yeah, I don't know why it's so hard to write anymore. And it's probably because I haven't been doing this for a while. The last time I did it was also a pain. Next time. Okay. So another way to write this is to try to just write out everything I know about this continuity equation in my head, which another way to write this is density t. This is the scalar derivative. And then you add that up with the statement of density, parentheses, I believe, is For the x direction, you use a u. So density u, you might see it in this format. And I hope it's following me. Like, if the recording isn't following me, then we're screwing ourselves. But density v1, sometimes you use that v1 plus density density. I'm using two different notation now. Wow, I'm such a shitty person. I am. I forgot that you can't use any. I forgot the two formats. Oh well, that's fine. I'll just show the other format too. Okay, here's another format that you can see that as this whole thing. Oh my god, such a mess. All right, another format you may see it is density. Density. No, erase it. All right, I'm writing everything I know about this so far. So density, density t plus density rho v1, density x plus density parentheses v2, parentheses 1 density x2 plus density. And you know why we're only going to 3? Because in the physical world, there's nothing beyond third dimension so far with fluid dynamics. So therefore, that's all of continuity. Everything I know about continuity. Summed up here. Well, continuity, actually, no, I take it back. There's one thing. Basically, what's saying is continuity means if you put in mass in, the same mass must come out. M dot, M dot. Basically, is what it's saying. It's not saying M is mass. Not M looks shit. I meant like this. You get it. I hope. Okay, the next thing we do is the momentum equation, which the professor writes it like this. So this one, my brain is saying to myself, like, why not try it? All right. Let's go with the momentum. Because let's just write what the professor wrote. Momentum equation here. It's gonna be a 3-hour long video. Density derivative v, you know. I love this big D. Like, I don't know how he did this in overleaf, but yeah, incredible overleaf work, man. Tablet. If you didn't know, my computer just my tablet just blinked out again. What is going on? But yes, I must applaud you on that one. Yeah, that was a good one. This is what the professor wrote. Okay. Momentum. All right, please, tablet, work. Okay. Yes, please, tablet. Don't fail me, please. You failed me like 15 times today. Please, tablet. Okay. So as you can see, you have oh my god, this tablet. Come on, work for me. Okay. Maybe you need new batteries. Never thought of the stylus needing new batteries, but yeah, this might cut off short. But basically, now let's go from memory. What is a big derivative? It's basically a commutative derivative. If I remember correctly, you should remember correctly. You did this like 20 billion times. So it's a derivative of v, the time derivative, which is acceleration term. And then that is plus by convective. So what this, oh my god, come on, please work, tablet. Anyways, combined by v dot gradient v. Yes. Now, oh, please, come on, stop, computer, stop. All right, this the tablet is giving my diabetes, aspirin, a headache. Okay, there we go. Now, the proper way to write this, right, is that v is equivalent to saying, no, please, come on. Equivalent to saying x, y, and then z, right? That is equivalent to saying that. And if you were saying that's equivalent, then this v is equivalent to saying dv dx dv x y. This is x, is y, dy, and then dvz. Oh my god, I'm so bad at writing. Sorry about the penmanship. I'm so shit, I know. And then we can see vx, vy, vz over here. And we can see over here that we have the long way, which is vx, vy, vy, vvz, vz over here, which is the dot product. And we see that that is equivalent to saying vx, derivative vx, dx. And I like to write it this way because I don't forget then. The other way to like memorize this, fuck no, I can't memorize this shit. I have to go from this over here to do this form over here. It makes it so much easier in my head, which is bad because it's not fast. A lot of people like fast, and I know I'm one of those people that likes fast. And I hate myself for not memorizing this. Like, it's so annoying that I haven't had it memorized yet. Yeah, sorry, that's a rant. Did I do this correctly? Let me double check. I think I did it wrong. Y momentum and Navier Stokes, right? Yeah. Yeah, I did it wrong. I think. Stokes. Yeah, I think I did it wrong. If I remember correctly, let me erase this thing. I think I did something wrong here. Yes, I did. Because this is not supposed to be here. That's why I wrote V purposely. I don't know why I added that term here because that is not supposed to be there. As we all know, it's V, not V. That. It's supposed to be like this. Sorry, my apologies. Yeah, and this is how I remember it. And this obviously then turns into a different form. Let me just grab this form over here. I hate this tablet, man. This is just giving me the worst treatment possible. So density, and then we have derivative v dt plus density parentheses. All right, so we have two different densities. So we have three different equations already from this argument. So let me just rewrite this, like the x direction, y direction so far. Yeah, so we have the momentum x-axis, and I'm just doing it from on this equation over here. I memorized this, I memorized this format, and now we're just what's the right word? Bringing it back from it. And we already know that this is true. Correct. Yeah. Now, my question is, am I this is the I think something's wrong here. I showed the full version of it. I think this is correct. But I know NASA has it another way where you pull this inwards, like this inside of here. Now, I don't remember why. So let me just bring this out in this notation and just really quickly show that's true, because the parentheses this I know why. This parentheses like this. So vi delta. Oh my god, tablet, please work with me. Please don't shit on my fucking it's working now. And then J, right? Free term. Let me see something. The time variant doesn't have an index because it's free variable. So it's free variable. There we go. All right. Vj dt, and then we know that as long as the dot product is true, you can move that over. So vi vj is true, and there we have it. So that states is equivalent to saying vj. So let me just erase this now, because we're gonna go into pressure now. Now we already talked about what this looks like, right? So we're just gonna copy that for pressure. So let me just y this dp pc. Notice that this p is all the same. That is important. That is the key of this whole thing. I don't think there's a difference. Let me double check this out. I might be just screwing myself over. Nope, I'm correct. So all the p's must be contained the same way. You are confused? Yeah, okay, that's fair enough. You can understand that later. That's how you can do it later. But yeah, you can figure it out later. We'll explain it later. I believe there's a negative sign here. But double check. There is a negative sign, and yeah, it's because the freaking tablet is making this like 10 times more painful. Like I can do this way easier without the fucking tablet. Now we have to deal with this stuff over here. Oh, you can do equations here? Never knew that. But we have to deal with this one next. Yes. Let me highlight this. That's just a notation. Okay, we're going to the next notation. Ij equal mu the scalar. Parentheses. That's the Vj by xi. And that's the way you do it. That's the transpose. And then plus parentheses. I think mu b is just there. And then 2 divided by 3 mu, that's just there. And this has to be like something like xi vi, right? By bj xi parentheses, right? Plus what? Is I don't remember. It's mu b, right? Plus 2 divided by 3 mu. Yes, that is correct. And then it is fudge. Fuck. I'm trying to do it, but I just gonna look it up. I also made a mistake here apparently from looking it up. All right, I'm looking at the PDF that the professor gave. Minus, right? And then we have oh, please work. Eraser. And then we have this, basically how you get that. But this part does not. So I have to figure this out right now. This has to go to 0 basically. Density V. Okay, so this is density Vi, density Vj, and then K. Oh, I'm stupid. I can't look this Vi because we have I and J as free variables, so I just fucked up here majorly. So let's just move this to K and I over here. Beautiful, right? Beautiful day. Over here we have to do I and J, and then this is X, not that, which means this is KK. Okay, we have I, so we have what we call delta X, delta IJ. Is this equivalent to 0? Is the question now. Yes. Okay, so what this is telling me is 1 is what equals to delta IJ, and then the derivative of that, which is the derivative of XI, which is let me just write this better. This looks awful. I'm pretty sure this is the reason why we have 1, 1, 1, right? And then this is we have when this is 1, so this is basically saying getting a vector out. I think it's getting a vector this way actually because of how the orientation is. So the vector is this way of derivative of 1 divided by xi, x1, comma derivative of 1, x2, comma derivative of 1, x3. So this is equal to 0, 0, 0. So we have 0. Cha-ching! I love that sound. My professor is going to teach this as cha-ching every time he got something. So I'm doing the same thing because when in doubt, follow up. One thing I learned